In this handout, we're going to analyze forced harmonic motion when the forcing is a sinusoidal function. And just to make it easy on ourselves, we're going to make our forcing term just a constant times sine of gamma t. So gamma right here it's a constant, but we're giving it a name, gamma, instead of picking a number, so that we can ask ourselves what happens for different frequencies of forcing functions. So gamma is just the angular speed of the forcing. Okay, so let's see what actually happens with this kind of situation. As usual, pause this video and work on these problems on your own, and if you got stuck, then unpause the video and you can see me work through these. Okay, so first find the complementary solution. So that's the solution to the associated homogeneous equation, which is m times y double prime plus k times y equals 0. So that equation, the characteristic equation, is m times r double prime plus k equals 0. So we get r double prime, this should be r squared. R squared is minus k over m, and so r is plus or minus square root k over m times I. And as I suggest up here, the traditional name for square root of k over m is omega. So let's call this omega times I. And that means our complementary solution is some constant times sine omega t plus some constant times cosine omega t. Now, this is the transient, but in this particular case, because the damping is exactly equal to 0, this transient doesn't actually go to 0 as time goes to infinity. That's not going to matter so much for the rest of this handout, but just keep in mind, in actual physical systems, the damping is never exactly equal to 0, and so this complementary solution, this transient, would go to 0 as time goes to infinity. Okay, go ahead and pause the video and work on number 2. Okay, so let's try number 2. Suppose that gamma is not omega and find a particular solution. So remember, gamma is the angular frequency of the forcing, and omega is the angular frequency of the complementary solution. So that's often called a natural, I'm sorry, I said frequency, it's angular speed. It's the natural angular speed of the system. So to find, since if we assume that gamma is not equal to omega, then comparing our forcing to our complementary solution, there's no overlap because because these constants in here aren't the same. We're assuming they're not the same for this situation. And so for our particular solution, we can just use sines and cosines with gamma t inside. So we get our particular solution is some constant times sine gamma t plus some other constant times cosine gamma t. Okay, remember our differential equation is y double prime plus omega squared y equals, I guess it's going to be f sub 0 over the mass times sine gamma t. Okay, so now we can start plugging in our derivatives. So we need 2 derivatives. So I won't write the second one, but I won't write the first derivative, but the second derivative is, let's see, it's going to be minus gamma squared A sine gamma t. Sorry, this should be cosine gamma t. No, that should be sine gamma t. I was right the first time. Minus gamma squared B cosine gamma t. Okay, so now we can plug these two y sub p's into the differential equation. We get, and let's gather up the sines and cosines. So for sine, y double prime contributes sine, so we get minus gamma squared A, and then y sub p contributes a sine as well. Remember, we have to multiply by gamma squared here, so plus gamma squared A. So both of those times sine gamma t. Okay, plus the terms that give us a cosine gamma t. And from our second derivative, we get a minus gamma squared b. And then from our y term, we get a omega squared b. So plus omega squared b. And the right-hand side of our equation is f naught over m times sine gamma t. Okay, so comparing the coefficients on our sines, we get that, let's see, omega squared minus gamma squared times a is equal to f naught over m. So that tells us that a is f naught over m times omega squared minus gamma squared. And for b's, or for the coefficients on cosine, there is no cosine on the right, but that means its coefficient is 0. So factoring out a b from this coefficient, we get omega squared minus gamma squared times b equals 0, and so b is 0. Okay, so our particular solution, I have sort of run out of room for the particular solution. Let me squeeze it in here. The particular solution that we got was f sub 0 over m times omega squared minus gamma squared times sine gamma t. Okay, there we go. Now pause the video and have a look at number 3. Okay, so find the amplitude of y sub p. Now in general, if you have a sum of sines and cosines like this, then the amplitude is the square root of the sum of the squares of the coefficients. But for our particular y sub p, since it doesn't have any cosines in it, right, the amplitude is just the amplitude in front of this sine function. So the amplitude is f sub 0 over mass times omega squared minus gamma squared. All right. Now have a look at number 4. Okay, so for number 4, if you remember back to number 3, I think, or number 2, we assumed that the frequency of the forcing, that is gamma, was not the same as the natural frequency or angular frequency of the system, which was omega. And that led us to the particular solution that we got before. But what if those two frequencies are the same? So what if you're forcing the mass spring system at its natural frequency? So that's what we're looking at here. So in that case, right, remember the complementary solution is some constant times sine omega t plus some other constant times cosine omega t. The right-hand side of our differential equation is f sub 0 over mass times sine of gamma t. So what we would normally choose for our particular solution in this case would be, right, remember in this case we're assuming gamma and omega are the same. So this gamma right here is actually omega in this case for number 4 here. And now there's some overlap between what we would want to guess for our particular solution, which is sines and cosines with gamma t inside. That overlaps with the complementary solution, which has sines and cosines with gamma t's inside, or I'm sorry, omega t's. So we know how to resolve that issue with undetermined coefficients. We just have to multiply by t. So we got c1t sine omega t plus, I'm sorry, not c1. We're doing undetermined coefficients, so usually we call this capital A. So capital A t sine omega t plus capital B t cosine omega t. Okay, so finding a particular solution in this case, right, actually doing undetermined coefficients, it's going to be extremely unpleasant. I'm gonna do it, right? We can do it together, but just we know ahead of time that this is going to be nasty just because all of the derivatives are going to have a bunch of terms in them. So this is going to be unpleasant. Okay, so first derivative, right, with this t in here, I can't do the first derivative in my head. So first derivative is, oh boy, a sine omega t plus, let's see, omega a t cosine omega t plus, and now derivative of the second term, b cosine omega t plus minus, let's see, we get an omega from the chain rule, so omega b t sine omega t. Okay, now for second derivatives, we got omega a cosine omega t plus, now I have to do the product rule on this mess, so omega squared a cosine omega t plus, let's see, minus, because we're going to differentiate a cosine, omega squared a t sine omega t. Okay, and this squared shouldn't be here, right? This term came from differentiating the t in here, and so there's no extra factor of omega. So this omega should be to the first power. Okay, plus, now we differentiate this cosine, so I guess that's minus b, we're going to get an omega from the chain rule, so omega b sine omega t plus minus, so now we're doing the product rule in this part, omega b, the t is going away, sine omega t minus, now an extra omega from the chain rule, so omega squared b t cosine omega t. Okay, yikes, what a mess. So we need to plug all of this into the original differential equation, right? So when we do that, there's going to be a lot to keep track of. So let's be as careful as we can here. Let's gather up all the terms that have a sine in them. So sine omega t. So let's see. There is, let me just underline those terms. There's this one, this one, this one, and this one. So this first one, coming from y sub p, we have to multiply that by omega squared. So omega squared a times t. Okay, times the sine omega t that I'm factoring out of all these things. So then there's the minus over here. There's a minus omega squared at. Okay, these cancel. Good. And then there's a minus omega b and another minus omega b, it looks like. So minus 2 omega b. All right. Now for our cosines. Terms with cosine, there's one coming from y sub p, and then from y double prime, there's these three terms underlined in blue. So from y sub p, we get omega squared b times t. Don't forget that we have to multiply this one by omega squared because the y term has an omega squared. Then from y double prime sub p, we have plus omega a. That's from this first one. From the second one, we have another omega a, so times 2. And then from the third one, minus omega squared bt. And that cancels the plus omega squared bt over here. That's good. And this is all equal to f sub 0 over m times sine omega t. Okay. So comparing coefficients on sine, we find, well, let's compare coefficients on cosine first, because b has to be 0. I'm sorry, a has to be 0 for this stuff in parentheses to be equal to 0. And then for our sine equation, right, comparing the coefficients on these sine functions, we get minus 2 omega b has to be equal to f sub 0 over m. And so finally, after all of this mess, we get b is equal to minus f sub 0 over m 2m omega. Yikes. Okay, so that means, let me borrow some space from number 5 here. The particular solution that we found was minus f sub 0 over 2m omega times cosine omega t. Sorry, times t cosine omega t. Okay, we did it. I think that that's right. If I made any algebra mistakes, please forgive me. But, you know, what we really need to know from this particular solution is that is the general form of it. So the coefficient isn't so important. What's really important about this particular solution is that it's either sine or cosine times t times some coefficient. Okay, so pause the video and have a look at number 5. Okay, so what happens to the amplitude of this particular solution as t goes to infinity? Well, you know, this looking just at the we can sort of rewrite this particular solution as t times minus f over 2m omega times cosine omega t. And when we do that, the amplitude of the stuff in brackets is minus f over 2m omega, right? So that's the amplitude of this cosine part, but it's getting multiplied by t. So as t goes to infinity, this amplitude of this particular solution, it goes to infinity because this, right, the stuff in brackets is finite, the t is going to infinity, and so the whole thing is going to infinity. It does have a cosine, so it's really oscillating, but the amplitude of that oscillation goes to infinity. So that means that this particular solution, it looks like this. So remember, this is what happened when we assumed that the angular frequency of the forcing was equal to the natural angular frequency of the system. In that case, the so-called steady state isn't steady. It actually is an oscillation that grows to infinity. This phenomenon is called resonance, and it's sort of one of the most important things about these sort of second-order constant coefficient systems. And we'll look into resonance more in a little bit.